Hello, my name is Jose Perez Padillo, PhD student at the University of Córdoba, Spain, and I am going to present you the work called Development of a Low-Cost Pressure Monitoring System for Urban Water Supply Systems. In many cases, water distribution networks, especially transmission networks, have a low efficiency. This is due to several factors. Many kilometers of pipes, there is limited information about hydraulic variables, difficulty in detecting leaks in pipes with difficult access. Thus, to improve the efficiency of water transport systems, our proposal consists in the implementation of a pressure monitoring system based on Internet of Things. The system detects leaks in real time so they can be repaired as soon as possible, improving the global performance of water transmission networks. In addition, the system gathers information about the behavior of the networks, what allows decision-making based on objective data. The architecture of a low-power and wide area network is simple. The final nodes collect the data recorded by the sensors and connect them directly to the base station to transmit the information and store it in a cloud database, where the data are analyzed and then sent to be visualized by internet-connected devices. The following diagram shows the proposed architecture for the pressure monitoring system. The system is based on the Internet of Things. The system has been developed using low-cost hardware and open-source software. An Arduino family microcontroller transfers pressure signal using the Sigfox communication network. The IoT ThinkSpeak platform is used for data analysis and visualization. Additionally, the system can send email alarms in real time using an external free web service called EFTTT when anomalous pressure data are detected. It can detect both faults and leaks in real time. The data collection device is composed of a pressure transducer and a set of electronics that transfer the signal to send it to the cloud database. The devices are prepared to use different telecommunication networks: Sigfox, LoRaWAN, Narrowband, GSM, or Wi-Fi. The one that best suits this work is Sigfox, based on radio communication. The device allows to connect several sensors for different variables simultaneously, although only one pressure transducer per node has been installed in this work. A more detailed description of the electronics is described in the article shown at the bottom. The system allows data consultation from any device with Internet access through its website. This facilitates database decision-making for the staff in the office and for maintenance personnel. The system emails warning when anomalous system performance occurs. This ensures a quick response from the water service staff. In addition to the water pressure measurement, the battery of the measuring device is monitored. The electronic components of the device are placed in a waterproof register box with an anti-intrusion and flooding sensor. The prototype developed was installed in a real water transmission system. The system supplies water to 44,200 inhabitants. The water transmission system consists of a total of 89 kilometers of pipe of different materials and diameters, as well as 18 tanks, 2 pumping stations, and a drinking water treatment plant. 3 pressure measuring devices were installed at different locations to test the performance of the designed prototype: a tank, a pump station, and an air valve. The different locations were selected to check if the prototype works properly under different operating conditions. In the pictures, the pressure transducer is highlighted in yellow and the data collection element is highlighted in red. In this slide, we have a general description of the 4 typical incidents detected by the proposed pressure monitoring system. The first type is the easiest to detect, a supply cutoff. The pressure goes from an optimal range to a pressure equal to 0 as a result of closing a valve. This operation does not involve water losses. The second type of incident is characteristic of a failure in the data collection component. Some sending cycles of data are not performing correctly for any reason. The fluctuation in pressure is accompanied by a fluctuation in the device battery. The third case shows the pressure evolution in a leak located downstream of the pressure measuring device. The sudden drop in pressure shows that a leak has occurred. The next period is critical due to the loss of water. The longer this period is, the more water will be lost in the leak. Once the pipe is repaired, the pressure will return to the optimum operating range. The fourth type of incident is like the previous one. In this case, the leak is located upstream of the measuring device. The following figure shows the pressure data for 1 month. 4 incidents can be distinguished in this pipe during this month. The system, besides detecting leaks, is also used to keep a record of them. The system can be used to control the operation of the pumping station. The analysis of the pressure variations allows to detect a malfunction of the pump and to correct failures. As the figure on the left shows, false pump start events have been detected. This could cause long-term pump deterioration as well as unnecessary energy consumption. In this case, the cause of false starts was identified, and a Renault signal from the tank level sensor that sent a start command to the pump control system. Another unusual operation was detected. The pump was running at 1 hour intervals. The situation was due to the existence of a leak in the distribution system. Therefore, the pump had to increase its frequency of operation to compensate it. The low-cost pressure monitoring presented herein has important advantages when compared to similar commercial systems. Robust system. The system has been successfully tested in a real case. Open source technology. The electronics used are based on open source and low-cost hardware. The investment is recovered between the first and second year. Modular and customizable. The elements could be edited, modified, or eliminated without affecting the global operation of the system. Versatile web platform. The web platform allows visualization and extra functions like data analysis, sending alerts, etc. On the other hand, there is a disadvantage. It requires specialized users. The system requires employees with knowledge of low power and wide area networks and knowledge about systems based on the Internet of Things. The future line of work consists of the creation of a web platform based on main 3 pillars: geographic information system, hydraulic model, and monitoring system, and the connection between them. Currently, the beta version of the web platform is being tested in a real case. Additional modules based on big data and artificial intelligence will be added in the following developing stages to create a smart water management system. Thank you very much for your attention. If you require further information, please contact us.